Another useful tool in discussing electricity and electric forces is something called the electric field. Now, the electric field is defined as the force on a small charge divided by that charge. So you can see the equation here. The electric field E is going to equal the electric force F divided by your charge Q. We're going to use lowercase q now to indicate something that we call, sorry, that should be a pen, to indicate something we call a test charge. Basically what it means is that the strength of that charge is irrelevant when talking about the electric field. Let me tell you what I mean. Let's say that you have a positive charge down here, somewhere down to the right, and we're looking here at this charge Q up here. Since they're both positively charged, that's going to cause them to repel. So you end up with this positive, this force that pushes little case q away. But if we have that same positive charge close to a negative, a charge negative q, then it becomes attractive and pulls it away. Well, in this case, in the first case, the electric field is going to be force divided by some charge positive q. And since we're dividing by a positive number, that means the electric field's in the same direction. But down here, you have an electric field equaling some force divided by a negative q, which means the force and the electric field are in opposite directions, as you can see drawn here in the figure. But then if you notice, again, comparing the two pictures, the electric field looks the exact same, whatever the charge is. So what I could do, let me draw another scenario here. If you have a positive charge here and some charge Q, you get some force that looks like this. But if you have some charge 2Q, the charge is twice as strong, therefore the force is going to be twice as strong. And yet, despite that, your electric field is still going to look exactly the same. So the electric field doesn't care about the magnitude or the direction of this charge here in the middle. It's a very useful tool, and so we're going to use it. Here's how we calculate it. We saw that the electric field is going to be force divided by the charge Q, but the electric force is going to be K times the product of the two charges divided by R squared. I just wanted to rewrite that for you just so it looks familiar. But you're dividing out one of those two charges. And so as a result, you get electric field equals KQ over R squared. Just like we did for the electric force, note that this is magnitude only. This equation for the electric field only gives you the magnitude. For example, you have a positive charge on some point over here. It's going to create an electric field in this direction. Whereas you have a point on the other side, it's going to create an electric field in the other direction. They have the same magnitude, but they're opposite directions. Therefore, this equation only tells us the magnitude of the electric field. Also, just to point out, remember you can also use the other version of K, which is 1 over 4 pi epsilon naught, which gives us this equation on the bottom. So this is how to get the electric field if you're given the force. But if you're given the electric field, can you get the force? Absolutely. The electric force would just be any charge Q within an electric field E. So let me tell you what that would be like. Let's say you have a positive charge here, and you have some electric field at this point, E. And then you say, okay, I want a more specific example. I'm going to place some charge Q equals, 50 microcoulombs at that one point. Then it's going to exert a force, and you calculate that force as the charge times E. Well, that would be Q times K big Q over R squared, where big Q is this charge, of course. That will give us what? K times the product of the two Q's divided by R squared gets us back to our electric force equation. If you have multiple electric fields at one point, let me show you what that might look like. Let's get, say, a purple. Let's say we have a negative charge Q here. So we have a red Q and a purple Q. Well, that electric field is actually going to be pulling, since Q is negative, since Q is negative, that's going to give me an attractive electric field, which is going to pull my electric field in here. Let's call this electric field 2, and the red one we're going to call Q1 and electric field 1. Then the total electric field is just going to be the sum of all the electric fields put together. Once again, electric field is a vector, so we are going to have to deal with vector addition for electric fields. So to solve problems in electrostatics, meaning static meaning stationary, electro of course meaning electrons and charges. So to solve problems with electric forces and electric fields, first thing you do is draw a diagram. Show all your charges with appropriate signs and drawing the electric fields and electric forces. Then we need to calculate forces using Coulomb's law, or if needed, electric fields using Coulomb's law as well, divided by the charge Q. And then we add the forces or the fields using vectors to get our result. So for example, if I have some positive charge Q1 right here, and I have some negative charge Q2 over here, and I want to know what is the electric field at this point in the middle, then I have to draw my diagram, which I just did, and I showed all the charges and points with their appropriate signs and electric force fields and forces. So we're dealing just with electric field right now. An important point to note about electric fields: if you have a positive charge, the electric field is going to point away, whatever the direction is. It doesn't matter where you are. The electric field is going to be pointing away. In this way, we can look at the electric field as a field of influence, hence why I got the name field. But around a negative charge, the electric field is going to be pointing inward. And that comes from the fact that, remember when we talked about electric forces, the equation for Coulomb's law itself just gives us the magnitude, but if you did it without the absolute values, you would get a positive or negative. A positive would mean repulsive, and a negative would mean attractive. It's the same for electric fields as well. That being said, your electric field due to charge 1, now we're showing all electric fields, that's where we are now. Due to charge 1, that point is going to have an electric field pointing away from the positive charge. So away from, looks like this, which means at that point, you're going to have some electric field pointing away. At charge 2, because of charge 2, charge 2 is negatively charged, meaning all electric fields are attractive, pulling in towards it. So All electric fields are pointing in, therefore at this point you're going to have some E2 pointing in towards Q2. And so there's the diagram. From there you're going to either use the electric, in this case we're doing electric fields. Let me write it this way actually. But you would use these equations to solve for your electric fields or your electric forces. Again, remembering the sign from these two equations only tells us if it's attractive or repulsive. To actually put them into vectors, you're going to need just the magnitude of these equations.